Today we're talking about solving absolute value equations, and much like what we were doing with the radical problems that we saw previously, where we had to isolate one of the radicals before squaring both sides, what we're doing with our absolute values is, again, we have to isolate that thing first. So think of it like a type of grouping symbols, and you don't want any multipliers out front, you don't want any other terms being added or subtracted to that. So these are already isolated, that's fine. But just make sure you do that first. Once that's taken care of, then we're going to rewrite this as two separate equations. And what we're doing is we're taking the expression 3x plus 7 out of those grouping symbols here and writing them as if there were no grouping symbols. And this is just the equation of a line. I mean, it's x to the power of 1, right? So what we're really doing here is we're saying 3x plus 7 has to equal 4, or that 3x plus 7 has to equal the opposite of 4. And the reason for that is because if you think about what the absolute value function looks like, it's your V-shaped graph. And when we're solving for x, what we're doing is we're finding the x-intercepts, right? And so you might have two x-intercepts. And so if you have 2 points, that means you should have 2 solutions. And so we get that by creating these 2 equations. Now it's possible that your V-shaped graph could be placed in such a way that the vertex is on the x-axis, which means you would only have one answer. So that's why we have to check for extraneous solutions. So continuing on here, let's move the constant term to the other side. I'm subtracting 7 from both sides, so 3x equals negative 3, and then x equals negative 1. Again, subtracting 7 from both sides, 3x equals negative 11, and x equals a negative 11 thirds. So those are the two answers, but are they the actual solutions? We have to do our check step here. We take those results and plug them back in. So we're asking the question, is the absolute value of 3 times my input of negative 1 plus 7, is that going to equal the positive 4? We're going back to the original problem. So what we have is a true statement, right? So absolute value 4 is 4. So yeah, that checks out. So absolute value 4 is 4, so that is a valid answer. What about the negative 11 thirds? So let's set this one up. Absolute value of 3 times the input of negative 11 thirds plus the 7. We want to know, is that equal to the 4? So again, we're going back to the original problem. We're not using the negative version of the 4. It's the original problem. Here you can see that we have 3 divided by 3, so those cancel out, leaving you with a negative 11 plus 7 in the absolute values, which turns into a positive 4. So yes, that also checks out as well. Both of these are valid answers. So if we were to graph this, we would have 2 x-intercepts. So in example number 2, we have a couple of twists, one being that we have an x squared inside the absolute value, and the other being that we have a variable on the outside. So instead of setting it equal to a value like 4, now the absolute value is being set equal to a variable instead. So let's see what happens when we take a look at these problems here. Again, we pull the expression out of the grouping symbols as we set up our 2 equations. So x squared minus 6 equals x, or x squared minus 6 equals the opposite of x. Let's bring all the terms to the same side. So x squared minus x minus 6 equals 0. It's a quadratic. So yesterday we talked about how do we solve a quadratic. You could use quadratic formula. You could complete the square. But these numbers are small enough that I think factoring is the faster choice. So we want factors of negative 6 that add up to a negative 1. So we want a negative 3 and a positive 2. Those multiply to the negative 6 and they add up to the negative 1. Separating our factors, setting each equal to 0, we get answers of 3 and negative 2. So we'll check those in a moment. Let me just solve both of these quadratics first. Again, bringing all the terms to the same side, we have x squared plus x this time with a minus 6. This also factors. We want factors of negative 6 that add up to a positive 1. So we want the positive on the 3 and the negative on the 2. Again, separating our factors, setting each equal to 0, and solving gives us answers of negative 3 and positive 2. So we have 1, 2, 3, 4 possible answers. And remember, with the V-shaped graph, we can only have at most 2 x-intercepts. So we know that some of these have to be extraneous. So that's going to be a lot of checking, and that's why these problems do take longer, but yeah, we have to check each one of these. So let's take the 3 and plug it back in. So here's our check step. We want to know, is the absolute value of 3 squared minus 6 going to equal, and again, this is my input as well on the right-hand side, will that equal 3? So we have a 9 minus 6, and that does give us the absolute value of 3, which is 3. So yeah, that checks out. So that's a valid answer. What about the negative 2? Absolute value of negative 2 squared minus a 6. Will that equal a negative 2? So we have a 4 minus 6. That gives us a negative 2 inside the absolute value. That turns into a positive 2 on the left-hand side. So you can see that it does not equal the negative 2 on the right-hand side, so that's extraneous. Let's try the negative 3. Absolute value of negative 3 squared minus the 6. Will that equal the right-hand side, which again is my variable, so we're plugging in that negative 3 there. So we have a 9 minus 6 is a negative 3 in absolute values. That turns into a positive 3. So as you can see, that fails as well. That's also extraneous. For x equals 2, 2 squared minus 6, we want to know, will that equal the 2 on the right-hand side? So this gives us 4 minus 6 is negative 2 in the absolute values, and that turns into a positive 2. So yeah, that checks out. So those are our 2 solutions. So let's take a look at one more example. I'm turning the page over, so I'm skipping over example 3 that's listed on our packet. And we're going right to example 4, because again, we're looking at some other variations of this technique, and that one actually kind of matches what we had done previously with the first problem. Let's take a look at something else. So again, we have an x squared in our problem, but something else that's showing up here. On the right-hand side, we have not just a number, not just a variable, but both, right? We have an entire expression. So you really want to think of this as a grouping symbol like this, because when we set up our 2 equations, we want to make sure that we have a positive version as well as the opposite of those 2 terms. So here's the first. We have an x squared minus 3x equals, as you see it, the negative 4x plus 6. Here's the alternate version, x squared minus 3x equals, so you have to be careful here, we want the opposite of everything. And so what that means for us practically is we will have to distribute a negative sign, a negative 1, to every term on the right-hand side. So be careful here. A common mistake is that I'll see students just change the sign on the first term and they won't change the sign on the next term. You have to change the sign on every term. So that's why I'm saying it's the opposite of each of these. Let's solve this first quadratic. We'll bring all the terms to the left-hand side. So I'm adding 4x to both sides. I'm subtracting 6 from both sides. We get x squared plus x minus 6 equals 0. And that's a factoring problem that we just saw in the previous example. So we're kind of borrowing the same numbers from before. We get these 2 answers. We get negative 3 and positive 2. I'll do the check step later. On the quadratic on the right, again, let's distribute that negative 1. So x squared minus 3x equals a positive 4x and then a negative 6. So again, we're moving all the terms to the left-hand side, so I'm going to subtract 4x from both sides. I'll add 6 to both sides as I push everything to the left. We get x squared minus 7x plus 6 equals 0. This also factors. We want factors of that multiply to 6 but add to negative 7, so we want a negative 6 and a negative 1. So each of these gives us those 2 answers. So we have a negative 3, a positive 2, a positive 6, and a positive 1. So again, 4 is too many. We know some of these have to be extraneous, so we're going to check all of them. So let's check the x equals negative 3 first. We'll plug that into the original problem that you see up at the top. We want to know, will the absolute value of a negative 3 squared minus a 3 times that input of negative 3 equal a negative 4 times the input of negative 3 with a plus 6? So here we have a 9. Negative 3 times negative 3 is also positive 9. So we'll have an 18 inside the absolute values. On the right-hand side, we have a positive 12 plus 6. So we get an 18 as well. So yeah, that does check out. That's a true statement. So x equals negative 3 is a valid answer. Let's check x equals 2. Putting that back into the original problem, we have the absolute value of 2 squared minus 3 times the input of 2 equals a negative 4 times the input of 2 plus 6. So 4 minus 6 gives us a negative 2 in the absolute values. Negative 8 plus 6 is a negative 2 on the right-hand side. Absolute value of negative 2 gives me a positive 2. So that one fails. So that's my extraneous solution. Checking x equals 6. Does the absolute value of 6 squared minus 3 times the input of 6 equal negative 4 times the input of 6 with a plus 6 on that? So 36 minus 18 gives me 18. Here's a negative 24 plus 6. So that'll be a negative 18 on the right-hand side. So that one fails. So that's also an extraneous solution. So most likely this value of 1 will be the final answer, but let's go ahead and check it just to make sure. Does the absolute value of 1 squared minus 3 times the input of 1 equal negative 4 times the input of 1 with the plus 6? So 1 minus 3 is a negative 2 inside the absolute values. Negative 4 plus 6 is a positive 2. We do get a positive 2 on both, so that's my final answer. So sure enough, it does work out. Those are the two solutions that we have here.